Let's compute the volume of a sphere using polar coordinates. So first we'll start with the Cartesian representation. That is, we're going to fix a positive number a and then write the equation in Cartesian coordinates for that of a sphere. That would be x squared plus y squared plus z squared equals a squared. And so now we can actually solve for the positive hemisphere, and that's going to be our surface. So we will define f of xy to be the square root of a squared minus the quantity x squared plus y squared. Now below the hemisphere, we have a disk in the xy plane, and that disk is symbolized right here. And in terms of Cartesian coordinates, we see that x runs from negative a to a, and then of course y runs from the negative radical here to the positive radical here. Now again, that's a very, very simple representation in polar coordinates. We can cover this entire disk if we let theta run from 0 to 2 pi, and then let r run from 0 to a. And that'll give us a simple polar representation of the disk here of radius a. Now, in order to make this particular calculation work, since we're only utilizing the upper hemisphere, we're going to need to double our result. So in Cartesian, we will double the result. We will let x run from negative a to a. We'll let y run from the negative radical to the positive radical. And of course, we have our surface dy dx. Now, we made the conversion via change of variables to polar coordinates. So our new limits will be 0 to 2 pi, 0 to a, and then of course we make the conversion for our surface where we replace x squared plus y squared with r squared. And now of course the area element dy dx becomes r dr d theta. So remember, r is the absolute value of the Jacobian. So what's interesting about these calculations, you get so used to this that you don't even think you're doing change of variables, but you are. This is just a very, very useful and important transformation in calculus. And so now, again, just like the last problem, we have a multiplicative result. These are constant limits of integration, so we can break this up into two integrals, and you can do them in any order you like. So first we have the 2, and we've got the 0 to 2 pi d theta, and then we have the r integral, 0 to a, square root a squared minus r squared, r dr. Now, of course, the first integral is very simple. That's just going to give us a 2 theta evaluated from 0 to 2 pi. Now, of course, we need to rig this. We've got our u du, but the chain rule says we need a negative 2r, and we only have an r. So what we'll do is we'll put in the negative 2 and then pay for it. So now this integral is table ready. Now, of course, this integral is just 4 pi. And now when we integrate here, we have the negative 1/2, but of course we add 1 divided by the new power. That'll give us a 3/2, and division by 3/2 will give us 2/3. Now, nicely enough here, the 2's absorb, so we just get a negative 1/3 times 4 pi, and then we just evaluate the antiderivative at the limits 0 and a. Upon evaluation at a, we get 0, that is a squared minus a squared, and then evaluation at 0, we just get a squared here. But of course, a squared raised to the 3/2 power will give us an a cubed, and of course we have the negative built in from the fundamental theorem. Now, of course, the negatives absorb, and we get 4 pi over 3 times a cubed. Now, when you look at that, that is actually the formula for the volume of a sphere. We're just accustomed to the a being an r. But now you can see that there are many, many ways to compute volumes of objects in geometry that you worked with in high school, that you worked with in pre-calculus. It seems like we do the same problem over and over, but this is an excellent example of how you can use polar coordinates to actually compute volumes. And we are done.